Hey, how's it going, everybody? This is Wesley with PV Prep. Just want to wish everyone a fantastic day. Today's topic is going to be on chemical equilibrium. I'm going to break down this topic into 4 different sections. The first video is going to be on the actual meaning of chemical equilibrium. The second video is going to be on this term called the K constant and how that influences the chemical equilibrium. The third topic is going to be on the reaction quotient, which is a concept that goes hand in hand with the K constant. And last but not least, the fourth video will be on Le Chatelier's principle, which is a very fancy sounding name of one of my favorite topics to cover in general chemistry. Okay, so let's get started, and we're going to jump right into the chemical equilibrium of a reaction. Now, in order to understand the chemical equilibrium, I think it's best to backtrack and talk about an irreversible reaction versus a reversible reaction. So I'm sure within your chemistry class, you guys have covered an irreversible reaction. This is a reaction that goes only one way, and usually you'll see it denoted with this arrow pointing to the right. Because remember, in general, in a chemical reaction, the left-hand side is going to be your reactants, while the right-hand side is going to be your products, right? So in this example, I have magnesium reacting with oxygen gas to form magnesium oxide. Now, on the other hand, a reversible reaction, you can tell by the name, is a reaction that can go either way. It's reversible, right? Not only can the reactants go to the right to form the product or products, right? The products can also go to the left to form the reactants again. And a reversible reaction is denoted with this double pointed arrow. So you're probably wondering why I'm going over these 2 different types of reactions. Well, it's because you need to understand a reversible reaction before you can understand chemical equilibrium, okay? So in order for a reaction to be in a chemical equilibrium, and by the way, chemical equilibrium is a state, okay? So in order for a reaction to be in chemical equilibrium, it has to be a reversible reaction, right? So it can form products and reactants and go both ways. It is a reversible reaction in which the rate of the forward reaction is equal to the rate of the reverse reaction. And at equilibrium, the concentration of products and reactants remains constant. So on the left-hand side of this system, I have a pizza maker as signified with the capital M. And on the right-hand side, I have a pizza deconstructor as signified with the capital D. As you can guess, if I put starting ingredients, which are pepperonis and sausages, into the left-hand side machine, this machine is going to crank out some pizza, right? So I put these guys in here. This right arrow represents, the process of making the pizza. And this rate is going at 3 meters per second. And once I make some pizza, on the right-hand side, the pizza automatically gets turned back into the starting ingredients, right? So you can see this kind of cycle that's going to happen here. I'll make pizza. As soon as I make pizza on the right-hand side, it's going to deconstruct the pizza back to the ingredients. And notice how going to the right, so making pizza, is the same rate as me going to the left, right? Which is the reverse rate right here. And it's the reverse rate is signified with a negative sign, which is just convention because you're going to the left. So I put in my initial ingredients, and notice that I'm only starting off with the pepperonis and the sausages, and I have no pizzas to start off with, right? I have nothing to put into the right-hand side. So just keep that in mind. We'll come back to that later on. And so let's say I put these guys in here, and then I step away for a little bit. After a certain amount of time, I come back, and what I notice is that there is a constant concentration of 3 pepperonis and 1 sausage, and a constant concentration of 1 slice of pizza, okay? And when I say a constant concentration, I mean this is in a dynamic equilibrium in which these ingredients here are constantly turning over into this pizza, and this pizza here is constantly turning over into these ingredients, right? It's not at a standstill, but overall, in the big picture, you're going to have a constant concentration of 3 to 1 to 1. And this entire system here is analogous to the definition of a chemical equilibrium, right? Let's go back and cross-reference everything. So a reversible reaction, right? Check. We have a reversible reaction in which you have a pizza maker that makes pizza, so going to the right, and pizza deconstructor that deconstructs pizza going to the left. So you can go either way. In which the rate of the forward reaction is equal to the rate of the reverse reaction. We have that too, right? The forward reaction is 3 meters per second. The reverse reaction is negative 3 meters per second. At equilibrium, the concentration of products and reactants remains constant. So after some time, right, this system, this pizza maker slash pizza deconstructor system, reached equilibrium, right, in which there is a constant concentration of pepperonis, sausages, and pizzas, right? And the constant concentrations are 3 pepperonis, 1 sausage, and 1 pizza. So one more concept that I need you guys to understand regarding the chemical equilibrium of a reaction is that it takes time for the initial ingredients to reach this equilibrium state. So that's going to bring us to the end of this video. Hope you guys have a better understanding of what it means for a reversible reaction to be in chemical equilibrium. And I'll catch you guys in the second part of this series.